This is a hypothetical particle called a tachyon. It's so fast that its slowest speed is light speed. As it blazes into the infinite, one can't help but wonder what things look like from its perspective. By now it's well known that as one moves faster through space, their journey through time slows down, with this effect being more prominent the closer we are to light speed. But what happens when we try to break the light barrier? In the previous video on tachyons, we were presented with the following scenario. We had 3 different observers watching a tachyon from 3 different positions. One perceives the tachyon going forward in time as it makes its way through space while he stands still. The second, who is moving in the same direction as the tachyon, perceives it to be traveling at a near infinite speed and then disappearing into infinity in the exact same moment. Then we have the third observer, who decides to go a little faster in the tachyon's direction, who perceives the tachyon to be traveling backwards in time. So, who is correct in this scenario? To answer that, let's take a look at something called the principle of relativity. The principle of relativity states that all observers, regardless of their relative motion to one another, will observe the laws of physics to be the same. So essentially, no one observer's observations are more or less correct than the others. Well, what about things from the tachyon's point of view? This is where it gets a little tricky, because nothing in the universe that contains mass like you or a rocket ship can reach light speed, or even exceed it. So everything that is about to be discussed is purely theoretical. This formula relates the flow of time for an object moving closer and closer to light speed relative to an object at rest. Now, let's say that we were accelerating in a spaceship that could travel at speeds far greater than the speed of light. As we inch closer to light speed, time for us begins to flow at a slower and slower pace until we hit light speed, which is when we would perceive time being frozen. To an outside observer, we would appear to continue zipping through the cosmos, not aging at all. However, for us, it seems like we arrive at our destination the instant we left, with no time lapsing in between. In fact, we wanted to take this moment to point out that the phenomena we explained in the time travel and wormhole video, with one end of a wormhole being here on Earth, and the other end being on a starship traveling at or near light speed, was poorly oversimplified. Assuming, for the sake of argument, we can ignore the weird mechanics of a wormhole with one stationary and one moving mouth, we would perceive the individuals in the spaceship as being frozen or nearly frozen in time. However, time in the universe is still running at a normal pace. For the individuals in the spaceship, their arrival and departure are simultaneous. So by taking a step through the wormhole into the ship, all you are doing is slowing the passage of time through you, but not the universe. It is technically still time traveling, just not in the way expected. Now that that's out of the way, it's time to ask the big question of what happens if we decided to make the jump to superluminal. Well, let's take a look at one possible scenario. If we set the velocity to be greater than light speed, we start getting imaginary numbers. If we factor this out and plot this on the graph, we see that at a certain speed above light speed, we get a time dilation factor of less than 1, meaning time might speed up relative to the time experienced by an object at rest. Again, this is only a speculation. It's also possible, as mentioned at the beginning, that some observers may perceive the tachyon traveling backward in time. But how exactly can this be? Well, it's important to understand that tachyons don't exactly work like you're used to. Normal everyday matter such as yourself gains energy as it approaches the speed of light and is in a state of what we call positive energy as it moves through time from the past to the future. Tachyons, on the other hand, are theorized to lose energy as they speed up, thereby putting them in a state of what we call negative energy. Now, if an object had negative energy as it propagated forward in time, it would be equivalent to an object with the same amount of positive energy moving backward in time. So essentially, this negative energy property of tachyons is what could allow them to be perceived as going backward in time without violating the principle of causality, which states that every real event has a cause behind it. Unfortunately, there's no way to test this, because the technology for faster than light travel and detecting a particle like a tachyon, if it even exists, is centuries or potentially millennia out of our grasp.